Good afternoon, and thank you for joining us for the 46th webinar in the Offshore Wind Series, Learning from the Experts. I'm Peter Lyon, Senior Advisor with NYSERDA's Offshore Wind team, and it's my pleasure to be joined by today's expert, Idalia Machuca with DNV. Before I introduce Idalia, a few reminders for participants and some background on the webinar series. Next slide, please. Firstly, if you're experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series are available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speakers. Next slide. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, then this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you'd like to suggest a topic or speaker for a future webinar, you can email us at offshore-wind@nyserda.ny.gov or fill out a survey also available on our website. Please note that all views and opinions expressed in this presentation are those of the presenter. Next slide. It's now my pleasure to introduce Idalia. Idalia Machuca is an offshore wind analyst in the Renewables and Power Grid Advisory Group at DNV, specializing in physical oceanography and meta-ocean and geophysical site characterization. Her focus in offshore wind project development includes subject matter expertise and project management related to innovation and digitalization, ocean numerical modeling, wind energy assessments, navigation safety risk assessments, and subject matter training. Idalia holds a Master's of Science in Physical Oceanography and a Bachelor's of Science in Geophysics from the University of British Columbia. Thank you, and I'll now hand it over to our speaker.
Awesome. Thank you so much, Peter. That was a really great introduction to the series and to this presentation. Okay, so today we're going to be discussing remote technology to support offshore wind operations and maintenance. Next slide, please. Okay, so we're going to be covering a variety of different topics today. I've broken down this presentation into two sections. One is going to be the meat of what we're going to be talking about, which is remote technologies. But before that, we've dedicated some time just to go through some background to contextualize the use of remote technologies. So first, we're going to set the scene looking at the state of offshore wind in the United States, looking at how based on the project timeline that we're expecting, we're going to be seeing this transition from very early stages of development through construction into operations. Then we're going to talk about the different offshore wind structures that you can see in an offshore wind farm and the anticipated changes, wear and tear that you might see in these various different components. And given this anticipated wear and tear that you might see in an offshore wind farm, well, what are the approaches that we can take to inspecting and performing maintenance tasks? And that'll lead us into some motivation for the use of remote technologies for these kinds of tasks. And with that, we'll step into a more detailed discussion on remote technologies. We're going to first look at the various different types of remote monitoring methods, then looking at some specific examples of remote technology. So we're going to be covering drones, crawlers, ROVs, which are remotely operated vehicles, AUVs, which are autonomous underwater vehicles. Then we're going to take these 4 different examples looking at their deployment methods. So how are these technologies not only used, but how are they launched? How are they deployed? From where? And then some select examples of their capabilities. And this is capabilities and applications within this offshore wind setting, and specifically looking at inspection and maintenance tasks. Given that background on these examples of remote technologies, we're going to look at some of their benefits, including benefits to safety, to operational efficiency, cost efficiency, and then looking at some limitations and considerations. So what are some of the technical and operational challenges that we might see using these technologies? And then given all that information, we're going to look at one of these technologies, which is the ROV in action. This is a very recent milestone. It was just published last week at the end of July. So this is very exciting to see, and we have a video that we're gonna see if we can play that for you all, which is really exciting. And then, given what we're seeing today, well, what can we expect in the future? So a lot of these topics that I'm going to be covering are, there's only so much that you can do in an hour. For a deeper dive, I'd recommend referring to a more detailed and more comprehensive report that we have prepared. So you can find this online if you look for remote technology for offshore wind inspection and maintenance, and you'll find it on BSEE's website. It's publicly available, and it's a great resource for anyone who would like more information about these various different types of remote technologies, and have some references to dig in a little bit deeper on their own time. Great. So with that, we're going to get started on background. Next slide, please. Perfect. Okay, so the U.S. offshore wind industry is rapidly evolving, with projects moving through various stages of development. What we're witnessing is a dynamic pipeline where projects are transitioning from the very early phases of development through mid-phase development into construction and finally into the operational phase. Currently, several projects are steadily moving through this development timeline towards construction and operation. This general pulse highlights the forward momentum of the industry. As these projects enter the operational phase, the focus shifts towards effective operations and maintenance strategies. So these strategies could use advanced technologies to support asset performance and longevity of these structures. Over the next few slides, we're going to be discussing how these strategies and remote technologies play a key role in maintaining safety, efficiency, and reliability of operations in these offshore environments. Next slide, please. As offshore wind projects transition into the operational phase, something important to understand will be the anticipated changes that offshore wind structures might experience over their lifespan. Offshore wind structures are designed to withstand a variety of environmental conditions, including harsh weather, saltwater exposure, and structural and mechanical stresses. However, gradual wear and tear are expected over time. Understanding these anticipated changes helps us understand and plan for the maintenance and inspection activities that will be needed to support the long-term durability and performance of these structures. The major elements of an offshore wind farm include the wind turbines, foundations, and offshore electrical infrastructure such as cabling and offshore substations. Above water components such as turbine blades and towers can experience surface erosion, cracking, and corrosion due to constant exposure to the elements. Below water components like foundations and subsea cables are subject to the effects of scouring, marine growth, sediment movement, and exposure to salt water and to strong currents. Having established the anticipated changes on offshore wind structures, it's important to understand and plan for how we can systematically address these potential issues as they arise. And that leads us into our next slide. Next slide, please. Effective inspection and maintenance strategies are guided by regulatory requirements, industry standards, and recommendations from the OEMs. OEMs being the original equipment manufacturers. These frameworks are important in maintaining compliance and upholding high standards and best practices in inspection and maintenance operations. Inspections must comply with 30 CFR Part 285, which is displayed on the right-hand side of this slide, which outlines the procedures and obligations for renewable energy activities on the outer continental shelf. The Bureau for Safety and Environmental Enforcement, BSEE, is responsible for enforcing these regulations, ensuring safety and environmental compliance. So beyond these regulatory requirements, industry documents such as standards, recommended practices, and service specifications provide additional guidelines for specific systems. These documents help define best practices for maintaining the integrity and safety of offshore wind components. There are two primary approaches for inspecting and maintaining systems. There's the prescriptive approach, and there's the risk-based or condition-based approach. The prescriptive approach is based on established requirements from previous experience and safety studies, following a set schedule and specifications. The risk-based approach uses non-destructive technologies to monitor and inspect assets, providing critical input to maintaining the offshore wind assets. This approach allows for maintenance and repairs to be conducted proactively during favorable weather conditions. These favorable weather conditions are sometimes referred to as weather windows. And you can perform these proactive maintenance and repair tasks during these weather windows instead of waiting for a fault to occur. Once we have a fault that has occurred, that could cause significant delays associated with weather conditions and increased downtime. Standards may suggest either approach or a combination of both approaches for certain systems. The approach and timing of inspections are largely dependent on the components being inspected. Other factors that play a role in determining inspection and maintenance schedules are the structural and functional criticality of a particular system, the evolving condition of the facility across its project lifespan, the potential consequences of structural issues, and changing conditions at the site. Inspections may also be needed following environmental events like icing, extreme temperatures, seismic events, or storms. Ultimately, inspection frequencies must adhere to the recommendations set by the OEMs and be informed by condition monitoring data. Next slide, please. Okay. Given the potential wear and tear that offshore wind components can experience, the various requirements and recommendations for their inspection and maintenance, it's clear that regular inspection and maintenance tasks are crucial to maintain the operational efficiency and safety of offshore wind assets. Traditional methods for conducting these tasks come with inherent risks, such as exposing personnel to harsh and potentially hazardous environments. Therefore, remote monitoring methods, could we go back to the previous slide? Yes, thank you. Therefore, remote monitoring methods and remotely operated technologies are increasingly being considered to conduct some of these critical tasks and to support personnel who are performing these functions. With the aid of these technologies, offshore workers can perform tasks more safely and efficiently. This approach leverages the skill and flexibility of offshore workers with the precision, consistency, and data-driven insights offered by remote technologies. Remote technologies can be employed in conjunction with condition monitoring systems, which provide continuous real-time data on the condition and performance of critical components. This integrated approach enables the early detection of potential issues and supports proactive maintenance of key components. In turn, this approach reduces the likelihood of unexpected complications that would require unscheduled repairs. Additionally, remote technologies are well suited to perform necessary tasks following severe environmental conditions like those that I listed previously, like icing, extreme temperatures, seismic events, and storms. Next slide, please. Given the potential utility of remote technologies in supporting offshore tasks, we'll now take a deeper look at the various remote monitoring methods available and explore the types, functions, benefits, and limitations of remote technologies. Next slide, please. Okay, before taking a deeper look at the types of remote technologies used for offshore wind operations, we'll take a moment to review the various types of remote monitoring methods that can be employed in the industry. These methods involve diagnostic and prognostic activities that provide qualitative and quantitative feedback on the structural and functional status of key components within an offshore wind farm. Displayed here is a list of the various types of monitoring methods, including visual inspection, radiographic inspection, ultrasonic inspection, thermographic inspection, infrared thermography, accelerometer vibrations, acoustic emissions, and so on. These methods use a variety of equipment, including cameras, sensors, and fiber optic cables to collect data from photos, videos, scans, and measurements. The data collected through these monitoring methods is processed and interpreted to diagnose and potentially prevent downtime associated with several types of issues. We'll now move on to some specific examples of remote technologies that use monitoring methods, and we'll discuss their applications. Next slide, please. Okay, the remote technologies that we'll be discussing are drones, crawlers, ROVs, and AUVs. These technologies have unique capabilities and applications that support offshore wind inspection and maintenance efforts. So first, drones. Drones are also known as unmanned aerial vehicles, and these are remotely controlled aircrafts that can be equipped with cameras and sensors for aerial surveys and inspections. In the context of offshore wind, drones can access hard-to-reach areas and capture detailed images and data to help detect surface damage, corrosion, and other issues. Okay, then on the bottom left, we have crawlers. Crawlers are robotic devices equipped with wheels, tracks, or legs to navigate complex surfaces and confined spaces. They can carry sensors and cameras to inspect interior and exterior surfaces. On the top right, we have ROVs. ROVs are remotely operated vehicles. So these are tethered underwater robots controlled by operators via a cable that enables data transmission and provides power to the device. These vehicles can navigate challenging underwater environments and are equipped with cameras, sensors, and even manipulator arms that allow them to perform detailed inspection, maintenance, and repairs on subsea components like foundations and cables. The tethered connection enables real-time control and data transfer, making ROVs well suited for precise and complex tasks in challenging underwater environments. Then on the bottom right, you can see an AUV. AUVs are untethered, self-propelled underwater robots that operate independently following pre-programmed missions. AUVs can cover large areas without the need for continuous human oversight, making them well suited for long-term data collection efforts. They can be equipped with various sensors for mapping, monitoring, and inspections. Over the next couple of slides, we'll discuss their individual deployment methods and also some applications within the context of offshore wind. Next slide, please. Okay, so we've had a brief overview of these various different types of remote technologies. So now we're going to be looking at how are these technologies deployed. Okay, first, drones. Drones can be deployed from vessels that transport personnel and equipment to the wind farm, offering flexibility and ease of access to various turbine locations. Drones can also be launched directly from the nacelle or from inside the hub of a turbine for immediate inspection of the blades and other components. Once launched, drones are controlled remotely, providing real-time video feeds and sensor data to operators. Drones are used to inspect turbine blades, towers, connections to the transition Ps, platforms, and ancillary structures above the waterline. Their high mobility and advanced imaging and video capabilities make them ideal for identifying external damage and corrosion, among other issues, quickly and systematically. Okay. Second, we have crawlers. Crawlers can be deployed from within the turbine hub to inspect blade interiors, or from the tower base to examine external surfaces. For external inspections at higher elevations, crawlers can also be lifted using ropes. Depending on the complexity of the task, crawlers can operate autonomously, or they can be controlled remotely by technicians, allowing access to difficult to reach areas without requiring personnel to climb the structure or to enter into a confined space. Given their ability to navigate confined spaces and complex surfaces, the capabilities that crawlers offer can be leveraged to detect both external and internal defects. ROVs. ROVs are connected to a surface vessel via a tether, which supplies power and facilitates real-time data transmission between the device and the operator. This allows for more precise control over the vehicle. Operators at the surface can use live feeds provided by ROV cameras and sensors to navigate and perform inspections. ROVs can be equipped with manipulator arms and other tools to perform minor maintenance tasks, like removing debris, adjusting equipment, and conducting some minor repairs. These capabilities make them useful for inspecting underwater components like foundations, mooring lines, and electrical cables. Lastly, AUVs. AUVs can be deployed from support vessels or from offshore platforms and can be programmed with specific routes and tasks. AUVs gather data throughout their missions, storing this data on board. They're capable of returning to a designated location for data download and for battery recharging. They can also perform extensive surveys and monitoring, reducing the need for human oversight. The types of data collected includes information on the seafloor topography, sediment composition, and the condition of underwater structures. Next slide, please. These technologies offer a wide range of capabilities and can be equipped with various tools and data collection for data collection and minor repairs. So here, we're going to highlight just a few examples of what these technologies can do to support offshore wind inspections and maintenance. Drones can be used for high-resolution visual inspections, offering an aerial view to detect surface defects and structural deformations. Drones can also perform ultrasonic inspections to measure material thickness and identify internal flaws within blade structures, for instance. They can also be equipped with tools for minor repairs on surfaces, such as fixing cracks and applying protective coatings. Crawlers can also be used for high-resolution visual inspections, providing detailed information of both internal and external surfaces. And what's important here is that we can get that very close proximity inspection of surfaces. Crawlers can also perform thermographic inspections to identify heat signatures and pinpoint areas of overheating and electrical components. They can also be equipped with robotic arms and grippers to carry out minor repairs, like applying protective coatings, sealing cracks, tightening bolts, making them a versatile tool for maintaining the structural integrity of key components. ROVs can be used for underwater inspections and maintenance tasks, using high-resolution cameras to capture images and videos of underwater structures. They can be equipped with sensors to conduct environmental surveys, and they can also be equipped with robotic arms and manipulators for handling objects, cutting ropes and cables, or performing cleaning tasks using brushes and water jet systems. AUVs are also particularly effective for underwater surveys and environmental monitoring. They can use sonar systems for high-resolution mapping of the seabed and various sensors for environmental monitoring. They can also use these tools to inspect underwater structures to identify physical damage, scouring, and marine growth. So, having explored some of these capabilities of remote technologies, we now turn to the potential safety, operational, and cost benefits that they can offer. Next slide, please. Remote technologies can enhance safety and improve accessibility. In offshore wind operations, personnel can face exposure to harsh weather and potentially hazardous environments. By integrating technologies like drones, crawlers, and underwater vehicles, we can reduce the frequency and extent of direct human intervention required to perform these operations in these challenging settings. Remote technologies can also significantly improve accessibility by allowing us to reach and operate in locations that would be difficult or impossible for personnel to access directly. For example, drones can assist technicians by performing inspections at great heights, and crawlers can complement operations by navigating confined spaces. Underwater vehicles can carry out inspections and repairs that would traditionally require divers to work in challenging underwater conditions. By leveraging these technologies, we can also extend the weather windows during which these tasks can be conducted. This means that these operations are less likely to be disrupted by challenging weather conditions. Therefore, maintenance and inspection tasks not only become safer, but also more consistent and efficient by avoiding delays. That leads us to our next slide. Next slide, please. Remote technologies can also enhance operational efficiency and improve data accuracy. These technologies facilitate continuous real-time monitoring, which supports early detection and resolution of issues. They're also well equipped to collect precise and detailed data, which supports informed decision-making for necessary or preventative maintenance and repairs. Drones, crawlers, and underwater vehicles can be deployed for immediate or long-term operations. For instance, drones can be quickly deployed to inspect turbine blades and identify any potential problems requiring immediate action. Crawlers can be used to continuously monitor the internal structures of turbines to identify issues before they become critical. AUVs can operate independently and gather data across a predefined path over an extended period of time. And ROVs can be equipped with a variety of cameras, sensors, and tools for precise operations. The data collected by these technologies is useful in making informed decisions about the tasks that are required to maintain the reliability of offshore wind structures. Underpinning these technologies is a data science approach known as CRISP, Cross-Industry Standard Process for Data Science. This process begins with an understanding of a project's needs and requirements. For offshore wind farms, for instance, operators are required to maintain the structural and functional integrity of offshore wind assets, as well as the safety of personnel. This understanding then leads to a more informed and intentional approach to data collection. Data can be collected through the remote technologies that we have discussed or through sensors installed on offshore wind components like wind turbines and foundations. This data can then be used to inform more robust data-driven models that help us understand the operational performance and the condition of offshore wind assets. Therefore, by using these kinds of processes, we can develop new solutions to improve decision-making around offshore wind operations. Next slide, please. As we have touched on earlier, integrating remote technologies in offshore wind operations can support our approach to proactive maintenance and as a result, improve cost efficiency. These technologies can be leveraged for early detection of potential issues, facilitating a condition-based approach to inspections and maintenance. By conducting precise, rapid, and consistent inspections, these technologies can help us identify and address problems before they escalate. This approach helps to optimize cost efficiency by minimizing operational downtime and preventing costly disruptions. The operational efficiency of these technologies also contributes to cost savings in the performance of these inspection and maintenance tasks. We've discussed the significant benefits that can come from integrating these technologies into operations. So up next, we'll discuss some of the additional considerations that we should be mindful of as we increasingly adopt these methods. And pictured on the slide, I just wanted to give a more realistic sense or a real world sense for what minor repairs or minor maintenance tasks can look like. So this is a photo. You can see a CTV in the background. So that's just representing the, the infrastructure needs that you have for operations. You can see this vessel out there in the background, and a technician strapped onto a platform on the offshore substation performing some, I believe it was maintenance on the paint coatings of the structure. Okay, next slide, please. Great. So, some additional considerations for the use of remote technologies. One of the key technical limitations that we see in many remote technologies is a restricted battery life. This can limit the duration of inspections and maintenance tasks, requiring careful planning for recharging the device. Additionally, there could be maneuverability challenges depending on the environments that these technologies operate in. For example, crawlers may face challenges in navigating uneven or slippery surfaces, and ROVs can face limited movement due to their cable connection to the vessel. Weather sensitivity is another factor to consider. High winds, extreme temperatures, moisture, and poor visibility can all impact the performance of these remote technologies. These limitations can delay operations and require contingency plans to manage weather-related disruptions. It's also important to note that the regulatory landscape for remote technologies is still evolving. As the application of these technologies expands, further clarity will be needed to ensure safe and effective use of these technologies. We have examined the capabilities, benefits, and limitations of remote technologies. Now we'll dive into my favorite part of this presentation, which is a case study showcasing one of these technologies in action. Next slide, please. Awesome. So we have a lot of really great pictures on this slide that were very kindly provided by the Center for Robotics and Intelligent Systems, Chris, at the University of Limerick. So a big shout out to that team for this amazing work and for letting us showcase their pictures. So what are we looking at? So recently, an ROV was deployed at the Windfloat Atlantic offshore wind farm off the coast of Portugal for inspection purposes. Windfloat Atlantic is the world's first semi-submersible floating offshore wind farm, and the ROV survey was conducted by a team of researchers at CRIS, the Center for Robotics and Intelligent Systems at the University of Limerick. The CRIS researchers have kindly provided these images to show the sea trials that they conducted at the Windfloat Atlantic site. The CRIS team operates a fleet of commercial ROVs and other in-house developed vehicles. Some ROVs in their fleet, which are also pictured on the slide, are used for support, such as for filming and for habitat monitoring. Also pictured on this slide is an image of the manipulators that can be installed on an ROV for probing and cleaning. So you'll see those pictures in the center of the slide, you can see those cool manipulator arms at work. The CRIS team has also developed a suite of software tools called Ocean Rings for positioning and control of these robots. Their ongoing efforts show a commitment to advancing technologies for inspection of offshore wind infrastructure. In the next slide, we'll share a video of the sea trials at WindFloat Atlantic showing the ROV in action. We'll try to see if we can, if we don't have any technical issues, fully appreciate the technology's capabilities demonstrated during these trials. So let's go on to the next slide and see if we can play this video. Nice. Okay, so here we are getting a shot of WindFloat Atlantic off the coast of Portugal. We're seeing that the objective of this trial, these sea trials, are to perform a visual inspection. This is the ROV that they deployed for the sea trial. Getting a little bit of background on WindFloat Atlantic and a close-up view of what the semi-submersible looks like. Ocean Rings, as I mentioned, is the control system, the software tools that they have developed. We see the researchers working live. Okay, so this is showing the DSLR camera images captured, a 3D reconstruction of the semi-submersible foundation. So this is really amazing, right? Because you can explore the structure while not necessarily being underwater. You can get a detailed view and manipulate the images captured. And then this is a 3D reconstruction of the columns of the semi-submersible, but this is using an aerial survey. Great, and that was a neat picture of the team out there. Must have been an exciting day. Okay, next slide, please. So as we look to the future, the rapid development of offshore wind is propelling innovation in remote technologies, further revolutionizing offshore wind operations. The current status of remote technologies varies, with some being commercially available and others in various stages of development. Significant innovations are occurring in two specific areas, one being the development of sensors to diversify and expand the payload deployed on these remote technologies, as well as as enhancing their autonomy in carrying out these tasks. The second major area of innovation involves digital tools and the application of data science principles to the processing of the data collected from not only remote technologies, but also other traditional methods like in-person inspections, condition monitoring systems, and the environmental monitoring tasks. Innovation in digital technology is poised to transform the industry through advanced techniques and data processing, machine learning, artificial intelligence, virtual reality, numerical modeling, digital twins. The integration of data-driven technologies will enable a holistic, or is expected to enable a holistic assessment on the condition and performance of offshore wind assets, which will then be used to support risk-based planning and therefore anticipated to reduce unplanned downtime and improve asset reliability as well as worker safety. Okay, and with that, that concludes this talk. Next slide, please. As I mentioned before, for anyone interested in a deeper dive into these topics, You can find further discussion on a comprehensive report that we worked on with Bessie. And you can find that online if you look up remote technology for offshore wind inspection and maintenance, or you can find my email address on this slide. Email me if you'd like a link to this document that you can find online. But yeah, happy to take questions.
Dalia, thanks so much for that presentation. It's exciting to see some of the cutting edge innovation that's happening between autonomous vessels and being integrated into practical solutions to service offshore wind farms. So thank you again for that presentation. It was great, and DNV always does a terrific job. So we do have some questions that have come in. The first is related to the drone crawlers, which can fly to a blade. Um, so are there drone crawlers which can fly to a blade that then attach and then crawl, or are
Oh,
they flying and inspecting, as they move around the blade?
I wonder if this question is it about a hybrid drone crawler?
It could be.
It
The
could
innovation
be.
never stops, does it?
I'm not aware of that hybrid idea yet. I might need to look that up to see if it exists or if it's under development, but that would be amazing. I might be a little bit concerned. So, something that I have seen that is a consideration for the capabilities for drones is, I mean, you're trying to get as many tools and sensors on the drones, but it needs to stay stable, right, in the air, and that's related to its weight. So it maybe that is an option to have a crawler drone, but I think there would need to be just some engineering to consider its weight. There's also various different, I mean, heavy, large drones do exist, but then that also gets into potential regulatory considerations, right? So, for instance, the FAA has specific regulations on the weight of a drone. So yeah, I love the idea. I wonder if it exists, but I'm sure that um, it's quite involved to make it uh, a reality.
Should probably get some engineers on that, it sounds like.
I sign up.
So the next question is, for drones, what is the typical battery longevity? Do the logistics of having to recharge the battery add significant complexity and time to the inspection/repair tasks, such as doubling the time for the task?
Yeah, that's a really good question. I think it might depend on the specific. So right now, what we're seeing, and this is just a general comment about remote technologies, is that there are so many different designers and different companies working on their own um, design and their own solution. Um, and it's still a bit unique to the individual designer. So there still needs to be, well, as we start adopting these technologies more, we're going to see some more standardization. So I think it still varies depending on the type of drone that you go with. But that is definitely a consideration because ideally, you would launch a drone and let's say on one duration of the battery life, you could inspect multiple different turbines. Um, but that depends on the distance that the drone is going to be flying between turbines and also the duration of the inspection for each individual turbine. And that also depends on the weather conditions. So if you're working in high winds, it's going to take more battery life for the drone to maintain its stability and to perform the tasks. So I think it's highly variable. Um, but I did see that in one of the manufacturers of drones, they have a comparison of how much time it would take to perform an inspection for one turbine, and it was, I can't remember the specific number of hours, but the comparison was, oh, this would have taken an entire day for a technician to do that by himself or herself, to do that inspection. Um, so yeah, definitely something to consider. Um, Not sure on this on the specifics because it might depend on the environmental conditions and on the design of the drone.
It sounds like it could be different in every circumstance, given, its interaction with the environment, wind conditions and whatnot. The next question that we have, where does the data collected by these remote technologies go, and how are developers made aware of any identified issues?
Yeah, and this extends from this concept that there is still there's going to eventually be a need for standardization across these different technologies. I mean, we're still working on standardization just in the offshore wind industry itself. So as you can imagine, this burgeoning um, innovation field will also go through that. So right now, what we're seeing is that many of the technology developers have their own suite of software, and that might include data storage. So data storage across all domains is a heavy consideration for whatever you're working on. Um, some of them are cloud-based. That's what we're seeing um, momentum in. And the reason why storage in the cloud is heavily considered is because of the capacity to hold um, big data, right? So you're getting so much data, especially when you're looking at photos and videos and sensor data, maybe a time series of data. You're looking at so much data. So that's going into storage. And then depending on the type of software that is associated with that technology, um, operate the wind farm operators or the developers would be capable of seeing, let's say, like a dashboard. If they have a control center, like a dashboard with alerts for depending on what they're interested in finding out. Um, the software could also streamline the reporting process, so they could, have that be more of an automated approach to getting, um, let's say, at certain time intervals, getting a report of the specific information that they're interested in seeing. Um, yeah, so there's a lot involved uh, after the inspections are done.
There's definitely a lot of data to analyze, whether it's in the development or the operation phase of these projects or the planning phase. So thinking about those different phases, there's a question that came in around AUV's ability to collect data on marine wildlife.
Mm.
So is that a way that these technologies are being utilized?
Oh yeah, totally. That's totally a thing. I know right now, this on the northeast on the East Coast, the Woods Hole Oceanographic Institute, WHOI, is doing a lot of work on that. Rutgers University is also doing a lot of work with AUVs. I mean, these remote technologies, think of them as carriers, right? So it's not just that the AUV or the drone is performing something on its own, but rather they're carrying a diverse payload. That's the term used for the different sensors and tools that can be equipped onto these technologies. And so, yeah, AUVs can be um, equipped with different sensors that can do not only physical oceanography, but that can also do some monitoring of wildlife, of biological and chemical aspects. And yeah, it depends on what sensors the operator decides to put on these devices. But ongoing innovation is happening in order to make sure that um, considerations like battery life, that battery life can be extended somehow, or that, you can have miniaturization of sensors so that you can load more sensors onto these technologies in order to capture more data. But yeah, it's multifaceted what these technologies can do.
A little bit of everything. So the next question is, related to the topic, but is more, thinking about the wind turbine generators and blades and cables themselves and towers. And so the question is, what are the most common occurring types of wear for fixed and floating wind farms?
Right. For fixed and floating wind farms, being in an offshore environment, what you see more often is, the most common type of wear, of course, is going to be corrosion, and also just because of like the nature of structures being out in the elements, you're also going to see fatigue. For corrosion, there's many different mitigation measures that you can take, including protective painting, or corrosion protection systems, and those are something that are some things that are actively considered in the design and in the manufacturing of, um, let's say, the foundations and the transition piece and the turbines themselves. Um, for fatigue is the term used for the repetitive loading that these structures experience. So as you can imagine, you have winds, you have waves and currents. So these are, acting on these devices. But again, the main mitigation measure here is the design itself of these structures. There's many different scenarios that are taken into account when designing these structures, and that includes that repetitive stress that you get from external factors. And then for floating wind farms, um, those are going to have mooring lines that anchor the the foundation to the seabed, and so you're going to see some more unique aspects there, given the the effects that you see on the mooring lines from currents. So you have some bending. Um, for electrical cables, you can also have some deburial from the seabed. So there's some nuances too between the fixed and the floating foundations, but those would be the most common types of wear that you might expect.
So getting back to drones, I just scrolled down the page of
Yeah,
questions here. We got some more. The question is, are there different regulatory requirements for use of remote technologies in state waters versus federal waters?
that is a good question. And the answer is it's unclear. So for instance, the for drones, the FAA oversees regulations of aerial vehicles. But from what I understand, there is some um, limit to the distance offshore over which the FAA has jurisdiction. And so there's still some things that remain unclear here, um, based on the regulations and on the definitions for the types of activities that are going to be conducted in offshore wind farms. Um, so I'm not sure, but I think that we are collectively not sure about what specifically applies in what situation within offshore wind.
Yeah, I think they're trying to figure this out in a lot of instances onshore as well as offshore when it comes to these newer technologies that are becoming more available. So the next question that we came in, I think gets back to the crawler umbilical question a little bit. So there are hollow portions of a blade. Are there hollow portions of the blade in which crawlers actually fit?
Yes, if we go to slide, wonder if we could go back to slide 13, the first slide of benefits of remote technologies. Oh, yes, that one. So that one, in the top figure, we see a crawler on top of the hub nacelle. You can see the blade sticking out on the left-hand side. So that's a crawler that's supporting an operation, something being performed by the technician. And then in the bottom, you actually see, so this is a photo of the testing of a crawler, one of the types of crawler technologies by Bladebug. And I believe that is a turbine that we're seeing the inside, we're seeing that cross section of a turbine, and we're seeing that crawler fit and navigate in that awkward position, but it's going through that structure. So yeah, totally. Those are the kinds of spaces that these technologies can help us inspect, where a human would have much more difficulty.
I was going to say,
Accessing.
I don't think I would want to squeeze in there. It definitely looks like a side profile of a blade. So,
Yeah.
one last question. Are wind farm owner operators using any of these technologies for surveillance slash protection of wind farms?
Oh, surveillance and protection. Is that that sounds like the person who's asking this might be asking more about security. That's a really interesting concept for an application for these technologies, because I think usually the maybe the type of work that I do, I mostly look at surveilling or like monitoring environmental conditions. But in terms of surveilling for human activities around these structures, I'm not aware of that particular function being used for these remote technologies, but it would certainly be interesting to kind of have a drone on standby, just performing surveillance, moving through the rows and columns of a wind farm, just checking everything out. I haven't heard of it, but it's a good idea.
Adalia, we cannot thank you enough for sharing your time with us today and your expertise on this subject. I'm sure you'll continue to receive several questions after this, via email, but it's definitely one that I'm super interested in, especially as we see more and more projects under construction and operation as the industry continues to grow here in New York and the United States. So thank you again for your time today. We
Thank
go to
you.
the next slide. And thank you to all the listeners out there for joining us for Learning from the Experts webinar. A reminder that the webinar is recorded and the presentation will be available on NYSERDA's website. Our next webinar in the series will be on October 16th. The topic is Health Sciences Experts from Ex Exponent. We'll discuss the assessment of health effects from electromagnetic fields. You can register for future webinars through our events page at osw-webinar-series.gov. We also encourage you to check out past webinars in the series on NYSERDA's website and YouTube channel. If you have any requests for future topics you'd like to hear about in the series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on our website. Thanks again, and we'll see you next time.